Hello everyone, this is Zhou from the University of Virginia. I'm going to present our work on strategic safety critical attacks against an advanced driver assistance system. As we all know, autonomous driving vehicles have been widely implemented on railroad all over the world recently. According to the definition by the Society of Automotive Engineers, there are 6 levels of driving automation, with level 0 meaning no automation and level 5 representing full automation. In this paper, we focus on level 2 advanced driver assistance system, or ADAS, which offers both automatic lane centering and adaptive cruise control features. It should be noted that for level 2 ADAS, the drivers are always driving and should monitor driving environment. One of the case studies we are interested in is OpenPilot, which is open source and supports over 150 car models on the road. In this presentation, we also use eco-vehicle or EV to represent autonomous vehicle or AV. The motivation to investigate level 2 ADAS safety is that most of the AVs are still at level 2, including Tesla Autopilot. Recent studies also show that over 3.5 million passenger cars worldwide are equipped with level 2 autonomous driving features. However, there are a variety of vulnerable components within a vehicle, including CAN bus, LiDAR, camera, or vehicle-to-everything communication. Malicious attacks or accidental faults could happen due to these vulnerabilities, which might cause accidents or threaten driving safety. Here, we present 3 example AV accidents involving car models by Tesla, Google, or Uber. Due to failures in detecting pedestrians or other vehicles ahead in time, more AV accidents or disengagements are also showing in the report of database of California DMV. So it is very important and urgent to thoroughly test the ADAS before it is used by the customers. The technical problem is to find the most safety critical scenarios from the fault or attack parameter space, such as the activation time, the duration, or other value as efficiently and realistically as possible. However, existing solutions suffer from their own limitations. For example, railroad testing in industry practice is time and resource consuming, as well as with high risk to vehicles and human drivers. Other works relying on simulations in AV literature mainly focus on level 3 or higher autonomy, while less attention has been paid to level 2 ADAS. In addition, they didn't consider driver intervention or use realistic control software well, and may need a large amount of training data, especially for machine learning-based approaches. To fill this gap, we propose a context-aware safety critical attack strategy that can find the most critical context during a driving scenario to activate faults that strategically corrupt the ADAS output with the goal of maximizing the chance of hazards and causing hazards as soon as possible before being detected or mitigated by the human driver or the ADAS safety mechanism. Our approach has the merit of exploring the fault parameter space, which is impossible to mine using random techniques, and using a model-based method that requires less training data than machine learning-based approaches. Although our approach is implemented as an attack strategy in this paper, its eventual goal is to find potential design defects of an ADAS and have safety checks for AV validations. To evaluate the performance of the proposed approach, we developed a closed-loop simulation platform with a real ADAS control software and a driver behavior simulator, and compare the effectiveness with several random attacks. This figure shows the overall control structure of an ADAS and the framework of the proposed attack engine. As we can say, our attack starts by collecting useful information through the inner vehicle communication and strategically corrupting the outward control commands like the amount of gas or brake by sending legal messages to the CAN bus. There's often a time gap between the activation of faults and the final propagation of unsafe control commands to the fixed layer, resulting in hazards. We define the time between the activation of an attack to the occurrence of a hazard as time to hazard, which indicates the maximum time budget for detecting anomalies and engaging mitigation actions. The driver reaction time is defined as the time difference between the perception of an alert and the start of the physically taking an action, such as hitting a brake. In AV literature, this time is reported to be 2.5 seconds on average. We define the mitigation time as the time it takes for any mitigation actions, such as braking, to be completed. A successful attack could cause a hazard at least before the mitigation action is completed, or even invade the detection of ADAS safety mechanisms or human drivers. On the other hand, for successful mitigation, the corrective action should be completed before the occurrence of a hazard. We consider three types of accidents: collision with the lead vehicle, foreign vehicle, or roadside objects. The hazards that may result in this accident include AV violates safety foreign distance with the lead vehicle, AV decelerates to a complete stop while there is no lead vehicle, or AV drives out of the lane. To increase the chance of hazards, we adopt a control-theoretic hazard analysis method to identify the specific combination of system states and the control actions that most likely leads to hazards. Here we show an example safety context that describes unsafe system context under which specific types of control actions may be unsafe and leads to hazards. For example, law 1 states that when the headway time is less than a safety limit and the AV speed is faster than the lead vehicle, an acceleration control action is unsafe as it will result in a forward collision with the lead vehicle. The attack goal is to maximize the chance of hazards while minimizing the time to hazard to evade detection. We formulate this as an optimization problem as shown in equation 1. The attack value must be within limits checked by ADAS safety mechanism and not noticeable to a human driver. We estimate the speed at the next time step by assuming linear acceleration for a short period, which is further updated using a command feature. To implement a context-aware attack strategy, the attacker needs access to the sensor measurements or the information shared through the inter-vehicle communication network to estimate the current state and the capability of modifying the actuator commands with 4D data. Possible entry points for executing such malicious actions include wireless networks, CAN bus, or the vehicle-to-everything communication. As shown in the overall framework figure, our attack procedure includes 4 stages: collecting information, inferring system context, selecting attack type and activation time, and corrupting the output commands. Fourthly, as shown in the figure, the attacker listens to the sensor circuit or the inner vehicle communication network, decode the message passed among software components, and extract the sensor data and the critical state information. Next step, more complex and human interpretable state variables in the safety specification, such as headway time, will be inferred based on the sensor data. The attacker then checks if the current system state matches any of the critical state contexts we previously defined in the context table to infer the attack type and activation time. Finally, the attacker strategically corrupts the control commands to not exceed the safety limits to evade detection, and encode the error value as well as new checksum into the CAN circuit in a legal format that will be sent to the electronic control unit of the vehicle, as shown in the figure. We developed a closed-loop simulation platform with a real ADAS control software and a color urban driving simulator. As we can see in the figure, the control software is the same as what is used in actual cars. The only difference is that as we are in the simulation, the Panda safety check module is not activated without hardware support. Also, the radar is not integrated. We also designed a driver behavior simulator and a fault injection engine to evaluate the effectiveness of the proposed attack strategy. During the simulation, the Eagle vehicle cruising at 60 miles per hour from a different distance away approaches a lead vehicle that cruises at a high speed or low speed or that accelerates or decelerates in the middle, to simulate different safety critical pre-collision scenarios identified by the National Highway Traffic Safety Administration. Examples of the user interface of a color simulator, OpenPilot, as well as a collision scene are shown in the figures. The simulated driver is alerted when the ADAS raises any safety warnings or the driver observes any anomalies in the vehicle, such as hard brake, unexpected increase in acceleration, steering angles, or speed. For hard brake anomaly, the simulated driver will stop the brake and output the regular gas amount without changing the steering angle. An emergency brake will be issued as a reaction to other anomalies listed in the table and forward collision warning. Driver's reaction to other ADAS warnings is not implemented in this paper. The driver physically takes an action after 2.5 seconds to process an alert or anomaly. We modeled the braking behavior as equation 4 to approximate the braking curve reported in a previous study as shown in the left figure. As shown in the table, we designed 6 types of attacks, including acceleration, deceleration, steering left or right, or their combinations. We also designed 3 random baselines. For random SD, we randomly select the attack activation time while fixing the duration as 2.5 seconds, which is the average driver reaction time. For random DOR, we randomly select the duration of an attack with the start time informed by the context table. For random SD and DOR, we randomly select the start time and duration. For all the baselines, we fix the attack value to be the maximum limit defined in OpenPilot. For context-aware attack, we strategically crop the output to not exceed the safety limits checked by ADAS safety mechanism to invade detection. This table shows the system resilience under normal operation or against each attack strategies. We see that under normal operation, no hazard or accident happens, but 2 alerts were raised due to the steering angle exceeding the predefined safety limits in OpenPilot. Also, lane invasion happened without any attacks. This figure shows the ADAS didn't always keep the vehicle in the center of the lane, indicating the automatic lane centering and adaptive control system do not cooperate well. For the performance of each attack strategy, we see that the context-aware strategy outperformed 3 random strategies and achieved the highest hazard coverage, with the most hazards occurring without any alerts. In these cases, the alert raised by the ADAS is a still saturated warning, while the more relevant forward collision warning is not activated, as the brake output is kept less than the safety threshold of OpenPilot. We further evaluated the effectiveness of each attack strategy in exploring the fault or attack space as shown in the figure, with solid dots representing hazardous cases. We see that an attack does not result in any hazard if not activated within a critical time window, for example, after the deadline at about 24 seconds in the figure, regardless of how long the attack lasts. After finding the critical launch moment, the attack needs to last for a time period, for instance, at least 1.5 seconds here to cause a hazard. Therefore, it is very important to find both the opportune time to start an attack and the required duration to increase the chance of hazard. We also observed that the context-aware strategy marked by orange diamonds are all solid and located within the critical time window. The dots that correspond to random SD and random duration strategies result in a large number of empty boxes. This further attests to the efficiency of the proposed context-aware strategy, which it doesn't waste resources on injections that result in non-hazardous states. An example of the system trajectories of each attack strategy is also shown in the figure. Then we evaluated the performance of each attack with driving intervention. As we can see in the table, most accelerations or deceleration attack were prevented by the simulated human driver, indicating the importance of human driver intervention. For timely hazard mitigation, the time to hazard should be larger than the driver reaction time. However, the driver reaction does not prevent steering attack, as the time to hazard is too short for a human driver to take an action. We also observed that the driver intervention may also introduce new hazards. For example, to avoid a collision with the lead vehicle, the eagle vehicle may stop in the middle of the lane, causing a rear collision or collide with the curved object. After adding strategic value corruption, even though there is an increase in hazard success rates, the total number of alerts generated by the ADAS decreases, and few hazards are prevented by the driver, indicating the effectiveness of the context-aware strategy for invading detection by the ADAS or the human driver. Here, we summarize the key observations. It should again be noted the broader impact of our attack strategy, which is finding potential defects in ADAS and helping improve safety checks. Thank you.